All right. Conjugation. Conjugation and aromaticity are put in the same chapter because you can think of aromaticity as an extended version or a high power version of conjugation. This out of the way. Here we go. All right. Right. We in chapter 3 we looked at valence bond theory in first semester chemistry. We ended the semester with valence bond theory and molecular orbital theory. So I hope in your previous life that you got a little taste of that before. Valence bond theory, the main characteristic of valence bond theory is that the electrons belonged to individual atoms. And then they were, to bond, they were just shared. Orbitals overlapped and they shared electrons. They still belong to the individual atoms. In molecular orbital theory, it's more like communism, right? Everybody puts their electrons into the pot and the collective gets their energy level structure from that. Okay. We described valence bond theory. We described sigma bonds, single bonds, sigma bonds. And then if necessary, this is one of the tweaks that was required. I don't know if I've mentioned this before. What do you do when a theory stumbles or even when a theory fails? You have three options. So reading. Remember that? Yeah. When a theory fails, you can tweak it. You can modify it. Or you can restrict its use. Right? So you know what your boundaries are. Mm-hmm. Or you can start over. There have been a few like that in history. Like, or get replaced, start over or replace. There may be competing theories out there that explain better, and then yours just drops out. Like the plum pudding model for the atom. Once Rutherford completed his work and proved that the atom was a nuclear based, then plum pudding just disappeared. But this is one of the modifications, this hybrid orbital addition to the valence bond theory allowed us to explain things like tetrahedral geometry for carbon tetrachloride or methane. Whereas the valence bond theory in its pure form couldn't explain that. And we knew the evidence was that all the angles of the bonds were exactly the same. So carbon comes in there with 2 electrons in s orbital and 2 electrons in the p orbitals. You can't overlap those to give you a uniform molecule with the hydrogens or the chlorines, as the case may be. So we needed to hybridize them into an sp3 hybrid with 4 equal sp3s. And we're going to be using hybridization in this chapter to help explain hate when this happens. To explain conjugation and aromaticity. All right, double bonds we know are made up of a sigma and a pi. And some of this terminology was retained in the molecular orbital theory. And a triple bond, of course, is made up of 2 pi bonds and 1 sigma. You always have to have at least 1 sigma on axis bond before you can add pi's to it. And pi's, of course, are if you have a sigma between 2 carbons, say, and then you need a double bond or a triple bond, then you have to have these, in the valence bond theory, you have to have these overlapping p orbitals. Okay, so that requires a certain type of hybridization. Right? It's just a double bond, then these carbons are sp2 hybridized. Okay. If it's a triple bond, then they have to be sp hybridized because you need these p orbitals, and then you need the ones that are going in and out of the board to overlap. Hang on to that idea because that's going to explain why conjugation can, we only find conjugation when you have alternating double and single bonds. You never have two double bonds side by side. You can't overlap them. Okay. I already mentioned that the pi orbitals are overlapping p orbitals. Valence bond theory is very useful and helps us understand molecular structures. That's without a doubt. It doesn't adequately describe species with electrons that are delocalized by resonance. And the reason for that is it goes back to the concept of electrons are shared but they're owned by individual atoms. So you either have to draw a sigma, a double, or a triple, no in-betweens. So you have to resonate between structures if you have two or more equal Lewis structures for a molecule. So delocalization, sometimes we represent delocalization as rather than this, if we're going to have something else out here, then we would put like that. Just show a partial bond. But that's a stopgap. That really doesn't do any explanations for us. So another tweak to the system is this concept of conjugation among the p orbitals. And then that will be extended to include aromaticity. Okay, later in the chapter, we're going to look at, take a glancing blow at molecular orbitals for two reasons. One is you don't need a lot of molecular orbital description to understand well enough to use the concepts of conjugation and aromaticity. If you want to go farther, then yeah, you do need to study molecular orbitals. And the other reason is I don't know them that well. So I would not be the best person to explain them to you. I need a guest speaker to come in.
So I'll see it in biochem? Or no, not really.
Perhaps a little. Maybe in the newest edition of Leninger, they might have molecular orbital discussion in there. I expect they will. Because it does explain some things that valence bond theory doesn't. Valence bond theory, or the localized electron model, really doesn't give you any information about energy levels at all. You can't do any calculations with it to determine it, whereas molecular orbital theory does.
Yeah.
Excuse me. And it helps you understand some more about not just the structure, but stabilities of the conjugated systems. We call them pi systems, or the aromatic systems. All right. I'd already mentioned that one. And then in chapters 16 and 17, well, 15, I left out 15. I did leave out 15. 15, 16, and 17, we're going to look at spectroscopy. And spectroscopy is Spectro refers to light, and oscopies means to look at. So we're going to look at light. And uh, actually, um, the spectroscopy, just as a descriptive term, covers a lot of ground. Right? It can be, you can do it in the lab, you can do it in the field, you can do it in the heavens. In fact, until we started sending probes out to other heavenly bodies, the only information we got was through light. We point our telescopes to the sky, and then first evidence was differences in colors that you see of the stars. Some stars are reddish, and some are bluish, and some kind of yellowish, like our sun. And then some inventive fellows, actually, I think they took somebody else's invention and used it in the telescopes to take the light that was coming from these heavenly bodies and spread it out and see what the various wavelengths were. And that's where we started to get real information about out there. We can do the same thing in the lab. And through the electromagnetic spectrum, there are various regions, and some regions give you certain types of information about a molecule, and other regions give you different information about a molecule. Now, the term spectroscopy has been expanded to include other things than light. And that's where we're going to go with chapter 15, mass spectroscopy. So there's not really any light there. It's just a series of data points that reference differences in mass of fragmentation products from your molecule. So you shoot it into the instrument. Well, I'll talk about that later. Okay. Later chapters than that, between 17, chapter 18 up to the chapter on our chapter 28, where we talk about polymers, we get more reactions. And I'm sure you're not going to be heartbroken that we missed those chapters. But they include reactions that involve conjugated systems and aromatic systems. I mentioned, I think the last time we talked in here, the reactions, aromatics like benzene, they do react. They just don't react the same way that you would expect with a double bond. All right, so there's the outline, and let's see. I don't think there's anything particular we need to say about that. We'll just jump right into it. Okay. Our first example is the cation of buta-1,3-diene. Now, this one can be, if we have that and that, they drew all the carbons in there, but I just assume not. If we have a positive charge there, then what's to say it doesn't occur on the number 1 carbon instead of the number 3 carbon? So that's where we have to resonate it. And what we're showing is that these electrons here go over there, and now we're left with a positive charge on this side. So we get that resonance, and one way to draw that is to say like this, like that. But that's one of the limitations of the valence bond theory. This is the only true way that you can draw a valence bond representation. And this is a stopgap to show you that it's a resonant structure. Okay. Now, what's going on here when it resonates? Well, in order to form the double bond, you have p orbitals here. So using that as our model. And you got an electron in each one. Let's make that one upside down. And then when these orbitals overlap, you get the pi bond. So we're not telling you anything new there. But the thing that gives this one a positive charge is the fact that it's got a p orbital and there's nothing in it, right? So that carbon has a hydrogen, and a carbon. It's got 3 bonds and it's deficient, right? So we've got, if we count out the formal charge, right? Carbon should have 4, and then it's only assigned 1, 2, 3 electrons. So we have a +1 charge, for a formal charge. Okay, so now we form the pi bond, and we've got a positive charge on a terminal carbon. What this model doesn't do is account for delocalization of electrons in a resonance hybrid. In other words, it doesn't actually show you, we can't use the valence bond theory to accurately show you this type of arrangement. So this is the artist's idea of what's actually going on here. We get an overlap of p orbitals. Excuse me, let me move that out of my way. And we have to look at them sequentially rather than as a whole. So this set of conjugated p orbitals is referred to as a pi system. And in this case, we have a single pi system. Single just means that as many carbons as you have in the system. Say we have a carbon chain like this, and we've got a double bond here and a double bond here. Let's just put another one down there. These would all be conjugated, right? We could easily write those as dash line here, dash line there, dash, 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 dash there. That would be a single system. Now, if that molecule went out here like this, and it skipped 2 bonds before it had another pi bond, this would be isolated from that system. So if we went ahead and did this, then we'd have a second conjugated system. So this would have 2 conjugated systems in it. This one has a single system. So that's what they mean by single versus double versus triple, multiple systems. Come on. There we go. Okay. What about stability? You know, if any process in chemistry, or physics for that matter, that proceeds spontaneously, only does so if you get an increase in stability for the product system. So we have to assume that if we're going to say this system is conjugated, that there's a return of stability for the system. So if we say, let's see, yeah, these species tend to be more stable if the valence, the p orbitals are conjugated than if they're not conjugated. So the one on the right doesn't show conjugation, but the one on the left does show conjugation, and it's more stable. And experimental data actually shows that the carbon-carbon single bond, well, it could rotate. I thought I read somewhere that it doesn't rotate. That must be, that was a different molecule. So scratch that idea. One thing you'll notice here, and we'll talk about this again later, is these p orbitals can't overlap unless they're parallel with one another. like that. So all the p orbitals in a pi system have to be parallel to one another and adjacent so that they can overlap, right? If they're perpendicular, they can't overlap. So if you get rotation around that sigma bond, then you're not going to get overlap between the p orbitals of this carbocation and its neighboring carbon. There's you get more stability, just a blanket statement by conjugation. Okay. Every atom contributes a p orbital. So you can't have one that feeds off the others. Okay? Everyone has to have a p orbital it can share. It doesn't necessarily have to have an electron in it, but it has to have an available p orbital. The number of electrons in the pi system is the same as the number of electrons that are delocalized in the resonance hybrid. That's a no-brainer, really. Right? You can't create electrons. You can't destroy electrons. So you have the same number in the pi system as you did in the individual resonance structures before you propose the resonance structures. You would have a hybrid system, more than likely sp2 hybrids probably. So you can count the electrons just by interconverting the resonance structures into our standard notation of the valence bond orbitals. And then you can count the electrons. We need to know how many electrons are in the system. That's going to lead us to an understanding of whether it's simply conjugated, whether it's aromatic, whether it's, I'll introduce a couple of terms, where it's non-aromatic or anti-aromatic. You have to know, one of the factors you need to know is how many electrons are in the system. Okay, here we have another cation, hexo-1,3-dienyl cation. Yeah. Okay, what's the question? Which atoms in the in this contribute p orbitals to the same pi system? Okay. Well, I look at the hybridization. I mean, Carty has an explanation here. He goes through his steps, but just looking at the system the way it is now, if we draw one more, and then we put our charge here, and then we have pi there and pi there. Okay, what's the hybridization on each of these carbons? Right, this one's sp2. Right? This one's sp2. So is this one. So is this one. Now, is this one sp2?
SP3.
Well, it's only got this carbon can only have 3 bonds to it to give you a positive charge. So that means there's one hydrogen here. Right? So if you only have 3 bonds to it, it's also sp2 hybridized. Yeah. But this one's not. This one's sp3. So we're getting contributions from these carbons right here. Okay. Now let's see how Carty works it out. How can you draw all the resonance structures of the species to establish resonance hybrid? All right. So there are the possibilities. This positive charge will, when we resonate, the positive charge doesn't go from here to here. It skips over there to here. So we can have a positive charge here. That means the double bond moves there. And we can have one here. That means the double bond moves there. So we have 3 possible resonance structures. And the way it's drawn there over on the far right, notice that we have dashed lines here, 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 and here, but not there. So we're only including these 1, 2, 3, 4, 5 carbons. All right. The electrons are delocalized over the first 5 carbons, right? We determined that already. So each of those carbons contributes p orbital to the same pi system. Yep. And this is a single pi system. because these are all connected in that system. And there's only one of them in that molecule. Okay. If we draw two resonance structures that are related by moving electrons over every atom for this cation, this requires moving 4 electrons as shown on the left. So moving 4 electrons. Yeah, okay. So I see what they're doing. We're using curved arrows, and we would get these moved over here and these moved over here. And that would give you your positive charge over here because you've taken those electrons and moved them. So now this one is deficient. That carbon's deficient. It has the positive charge. All right. Was that the question? That must have been the question. Oh, okay. Which atoms contribute p orbitals? Okay, those 5 atoms. How many electrons are in the pi system? Well, it says 4 electrons move. Is that how many we have in the pi system? Right. This one's going to be 1, 2. It's going to have 2 hydrogens. No, it's only going to have 1 and an unused. No. No, it has 2 hydrogens. This one has 1 hydrogen. This one has 1 hydrogen. That one has 1 hydrogen. And this one has the 1 hydrogen. Okay. So we have, if this is sp2 hybridized, that means we have this p orbital here and here are overlapping to give you that double bond. That's the way we would normally consider it. But if we contribute p orbitals, all of them, you have 1, 2, 3, 4, 5 p orbitals. We've got electrons here, 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 and this one's deficient. There's no electron in that because this is a positive charge. Okay, so that's right. We have 4 electrons that go into this system. These 5 carbon atoms, and we have 1, 2, 3, 4 bonds between them. So the way I look at it is, if it's conjugated, then you count the number of bonds to find out the number of electrons. Now, Cardi might disagree with that, but that's what it looks like to me. All right, let's see. Butyl-1,3-diene. Okay, this one I suspect is conjugated. Now, one thing we notice is this molecule is planar. Now, even though, no, it's got that sigma bond in the middle, and we would expect that it would rotate. This is where I got that idea before that I was down the wrong rabbit hole. This molecule will not rotate, probably because of steric hindrance, but also because we have conjugated the system. So now that we don't just have double bonds and single bonds, we have delocalized electron structure, and we have partial double bonds between every carbon. And that would keep it from rotating. The other thing we'll notice here, let me see if I've got comments. All right, does not have an atom. Okay, in this one, we don't have any formal charges. All right, they're all zeros. That's the one difference between this one and the previous example. So it doesn't show us the same type of resonance because we're not moving electrons and repositioning that positive charge. However, conjugation does explain 2 key features of this molecule. One, get this out of my way. You don't have to watch it. I probably ought to just, I'm going to do this. There, that's good. I don't need to see me. uh, the central carbon bond can rotate, its rotation is hindered. And we talked about that already. So this molecule is entirely planar. In order to get a conjugated system, it has to be planar because these p orbitals have to be parallel to one another. If anything rotates in here, now they're out of position. So that's a given. It's a planar geometry. Now, of course, we know it's planar because we've done the experiments also to confirm. In fact, I don't know which came first, the chicken or the egg. And the other thing we notice is the bond lengths. The carbon-carbon double bonds are longer than normal, right? Remember, well, maybe we talked about this in 101. In general, if you just have a molecule with a single bond between, say, two carbons, it's going to have a certain length, which is indicative of the strength of the bond also. If you put a double bond in there, it shrinks. And the bond is stronger and shorter. And put a triple, it gets short. Okay. So we expect a certain distance between two carbon atoms that have a sigma bond and those that have sigma and pi. However, the double bond in this molecule is longer than what we would expect. And the example there is given is this, let's see, what is that? Ethene, that ethene molecule. That gives you your standard for the double bond because there's nothing else for it to conjugate with. So it's 132 picometers. But the double bond in our butyl-1,3-diene is 133.8 picometers. It's longer. Right? So it's lost some of its pi character. Okay. Conversely, when we look at the carbon-carbon single bond, it should be a certain length, and the ethane molecule gives us our anchor, should be 154 picometers. It's actually 135.4. So it's gained some pi character. So that's evidence for the conjugation and the delocalization of electrons in this system. Okay. So we in this butyl-1,3-diene, we have four orbitals, four p orbitals, and each one has an electron in it. 1, 2, 3. Okay, so my idea before doesn't work, right? Count the bonds. That's the number of electrons. That only works when you have one of them is deficient, right? In this case, we have four p orbitals to overlap, to delocalize, and each one has an electron in it. So we actually have four electrons in this system. And since they're sharing their electrons across the entire system, that's what loses some pi character for the double bonds as drawn and gains some pi character for the single bonds. Right? Each carbon is sp2 hybridized and is uncharged. Right? We know that from valence bond theory. I mean, we don't have to look at any other theory. Valence bond tells us that. So each carbon contributes one p orbital, and to remain parallel and conjugated, that the molecule can't rotate, and it's more stable as a consequence of the conjugation. They all have to be in the same plane. And that allows for the pi orbitals to be delocalized. We're not delocalizing the sigma electrons. They're still in their sigma bonds. It's just that if we grant them some pi electrons in this delocalized pi system, then the overall, the sigma plus what else comes along with it, changes its bond length in bond character. Okay. Let me see. Right. So the takeaway is all three carbon-carbon bonds have pi bond character. That's one major takeaway from conjugation. Okay. So here we have, I mentioned the fact that um, if you have two sigma bonds between pi bonds, if you have two single bonds between the next pi bonds, then you have effectively isolated one conjugated system from another. Or in this case, the far left where you have that double bond, it's not conjugated with anybody. So if you were able to measure the bond length there, it would be what you would expect of a double bond. Whereas if the carbons on the right, we conjugate those three carbons, the number 2, 3, and 4 carbons. That is a pi system, and it's isolated from the other. Primarily because those carbons, those two carbons that are being pointed at right here in the middle, let's see, you won't be able to see that on your version, but those arrows point to those carbons. Those are sp3 hybridized. They have no pi orbitals, p orbitals to donate. Okay, how about this one? Increasing stability. Let's see. I think I've got some text to go along with this. All right. We haven't really definitively proved stability yet. We're going to get some experimental evidence to prove stability here in just a slide or two. But if we assume that conjugation increases stability, the outcome of a chemical reaction can vary depending upon whether the pi system involved is conjugated or isolated. So if we're going to use this tertiary butyl alcohol, well, that's the solvent. The tertiary butoxide ion is going to convert that bond where the iodine is located into a double bond. Right? You have to think way back. So, which one of these outcomes is going to be preferred? Well, the one that produces the most stable product is the one that's preferred. Right? So we get 65% where the double bond forms to the left of the iodine in this case, and a minor amount of product would form the non-conjugated system double bond to the right of the iodine where it was previously located. All right. Yeah, that's what that black and white says. I'm trying to make it conversational rather than just read the slides. That helps me. That helps me understand it too. Okay. So if we have two different types of pi systems, now the as long as you have p orbitals, whether they've got electrons in them or not, if they've got p orbitals that are parallel with their neighbors, then you can conjugate. So we can still get conjugation with a triple bond. In this case, we've got a double. Actually, we've got that cation on the end, which means it's sp2 hybridized, and we have an unoccupied p orbital that's available. So it's going to add to the system. And then we have that second carbon from the left. It also is sp2 hybridized. And then the next one is sp2. The one on the next carbon, though, has to be sp hybridized. does it not? If we have carbon here, carbon there, we have, yeah, carbon here, and a triple bond here, that one. What did we say? Well, this was in 101. Count the number of groups, right? You have one, two groups means sp hybridized. But that just means that you've used one p orbital and one s orbital to make this hybrid, right? So you get two equivalent SPs and they're linear. So you have one here and one here. But these guys right here are formed from unused p orbitals there and into the board and out of the board, or parallel to the board and into the board. So you still have those p orbitals available. So what you can do is, since these are on the plane of the board, then you can hybridize these right here along with these others. But these two can't be, right? So the sigma bond and one of the pi bonds remain untouched. And one of the pi bonds contributes to the pi system. That's what they're trying to show there. So you can still get resonance hybrids and conjugation with a triple bond. Now, I don't know if I muddy the waters if I do this. Right? What if you got, right? So that would be, just say it's this molecule. I know this molecule is this. We can talk about this. So this has to be sp hybridized. This is sp2, right? This is sp2. So this one has like that. This one has like this, but it also has into the board like that. So theoretically, you would think that we might be able to hybridize it. I mean not hybridize, conjugate that. Although I've never seen that happen. It's always been a single bond and then a double or a triple. So that's a question that I keep in the back of my mind until I find an answer. Okay. Let's see. In 14.4, we had two separate pi systems. We just left that slide, even though it has no tetrahedral carbons. This pi system has 4 pi electrons that are delocalized over 5 carbon atoms. Wait a minute, this species has 2 separate pi systems. Okay. I see what they're saying. Right, 4 of those, let's see, we've got the 2 and the 3 carbon. Well, actually, if we go from the other side, it's 1, 2, 3 and the 4 carbon have a single pi system, and the 1 and the 2 carbon have a double pi system. And there's one isolated pi bond that's not used. And I already mentioned that, so I'm not going to stay there. All right. What we're trying to demonstrate, or what Carty's trying to demonstrate on this other side, is the p orbitals that are in the conjugated system. And it looks like every atom in this molecule is conjugate, is part of the system. Yeah. Yeah, and he color-coded them, right? So the blue conjugating and the green ones can't because they're perpendicular. There's no overlap there with the rest of the system. All right, so that was the point of that one. So at most, takeaway, at most 1 pi bond from a given triple bond can contribute to a pi system. No more, just 1, no more. All right. Now here's the evidence. We studied hydrogenation. at the end of the last chapter. So we know how it's done, right? We've got double bonds and we got say platinum or palladium catalyst and hydrogen gas bubble through there. And we can get this reaction we can hydrogenate those double bonds, right? So the key here is that whether you have this hexa 1,3-diene, which based upon our previous understanding should be conjugated, right? Whereas the hexa 1,4-diene is not conjugated. Those double bonds are isolated from one another. We still get the same products. Right? We add 4 hydrogen atoms to both of them. Right? But the energy, this is exothermic reaction. The energy we get back is different for the conjugated versus the not conjugated. Right? So if the conjugated system is supposed to be more stable, that means it begins at a lower energy. And so if we proceed through this reaction progress, then we're going to get down there, we've got the same products over here, but this one is where the non-conjugated starts, and this is where the conjugated starts. Right? So it's going to go up here. I don't know if it has the same activation energy or not. Probably not. It probably goes up like this. It comes down here to the same place. Well, the difference here is less than here. Okay? And that's shown in the hydrogenation energies that you get back. Right? For the conjugated system, you only get, in this case, 221 kilojoules back. And for the non-conjugated system, you get 241 joules back. So this is a technique where theoretically, you've broken the same bonds for both molecules and produced the same product bonds. So if it were not conjugated, you would expect to get exactly the same energy. But since it's conjugated, we see that difference. And we use this heat of hydrogenation to confirm conjugation. All right. Well, there's Carty's explanation for it. Okay. For the non-conjugated system here in the middle, we have minus 241 kilojoules. If we had 2 separate molecules, one with a terminal pi bond and one with a pi bond on the 1, 2, 2, 3 carbons, like those two, and we put those energies together, then we get the same amount of energy back for the 2 separate molecules versus the one non-conjugated. Okay. That slide doesn't add anything to the discussion. Okay, what about conjugation in lone pairs of electrons? So now instead of, remember we started off with a cation. Now we've got one with an anion. That means this carbon has to have, right? It would have 2 hydrogens, right? 2 hydrogens. And a lone pair, because that carbon gets 1, see, starts off at 4, minus 1, 2, 3. It's going to have a negative charge. This has to be 5. So you have to have a lone pair there to give you a -1. So now we're starting with an allyl anion. Allyl is the term for 3 carbons. One of them's got a double bond and one of them's got a single bond. That's allyl. So, is this going to conjugate? Well, apparently it does. right? Because it will resonate. We show the curved arrows, and it's resonating between these two structures. And we show 4 pi electrons are delocalized over 3 carbons. And then below is Carty's drawing of the p orbitals. So in this case, it doesn't show them. 4 electrons in p orbitals. Now, how do you do that? Well, oh yeah, okay. A single p orbital can have 2 electrons in it. Yeah, you can do that. Okay. Oh, this one has a special name. No, it doesn't, because we're on a different molecule now. We don't have carbon anymore, and now we got oxygen down here. Right? Got an oxygen there. And this oxygen has a negative charge. That means it has a full complement. Well, oxygen is 6, right? In valence electrons. So we have 2, 4, 6, 7. That's where we get the -1. So we have 3 lone pairs around that oxygen. And it resonates with an enolate type anion. So it will resonate to take the charge away from here and put it over there. And then the double bond is over here. So we make a carbonyl on this side instead of an ene on that side. Okay, where are those lone pairs located? Well, this oxygen is not hybridized. I don't think. Doesn't need to be hybridized. But it has unused, let's see, perpendicular. All right. 2 of those lone pairs don't participate because they're not parallel, right? All 3 atoms are sp2 hybridized. Okay, so this one is sp2 hybridized. sp2, sp2. And these, say, let's pick these 2. These are in unused p orbitals. And this one has used if it's sp2 hybridized, let's not do that one. sp2 hybridized should give it 3 equivalent orbitals and then 1 unused p orbital, right? So 2 of these electrons are in that hybridized orbital, and 4 of them are in unused p orbitals. That's where they're located. Acetaldehyde. Now, where did we get that name? Well, what's acetic acid? That's where I start. CH3, C, H, right? Okay. The aldehyde then would be to replace that OH with a hydrogen. That's acetaldehyde. So that's what you got on the right. And it resonates with an enol on the left. Okay, let's see. Oxygen contributes 1 lone pair of electrons to the acetaldehyde enolate anion pi system. Okay, I'll go with that. The other 2 lone pairs occupy sp2 hybrid orbitals that are perpendicular. Therefore, they're isolated. They cannot participate in the conjugated system. All right. So an atom can contribute at most 1 lone pair of electrons to a particular pi system. All right. We looked at a previous one where we had triple bond. That carbon could only contribute 1 p orbital to the system with its lone pair, with its pair, not lone pair, pair of a bond. And if we have an atom that can contribute lone pairs, it can only contribute one, right? Because that there's only one orbital that can be parallel with the system. The rest of them are perpendicular in 3 dimensions. Okay. So let's see. We're going to get into cyclic pi systems. Benzene as an aromatic compound and cyclobutadiene as an anti-aromatic compound. All right. So now we're going to let's talk about Auguste Kekule. The story is, I don't know if it's true. The story is nobody understood. They knew the compound was this and that. They knew the formula, but they didn't know the structure. And they tried to draw all kinds of different structures, linear structures, branch structures, to try to get that as part of it. And the story is that Kekule, either in a daydream or at night in bed, he dreamed of this snake. So this 6-carbon snake, 1, 2, 3, 4, 5, 6, wrapping around and grabbing its own tail and forming that system with a hydrogen on each one of the carbons. Now, in order to do that, right, they knew at this time in the mid 1800s that carbons had to have 4 bonds, right? So they had to do like that. So that was Kekule's contribution. This was benzene with his tail grabbing snake.
Who deems this stuff like correct though? Like who says this is it and this is what we're going to do? Like, 'cause that's what I don't get. Like, how did we come up with this stuff and who said working about this stuff?
A lot of people. A lot of people proposed explanations for real phenomena. And then it's up to the scientific community to try to tear them down, right? And if you can't, because you can't prove a positive, you can only maybe disprove a negative. So you propose your theory and you say, this is what I believe is happening. And it's based upon real world experimentation, right? I've said it before, nature just does what it does, and we've got to explain it. So people come up with explanations, and then the rest of the scientific community that has expertise in that field will go in and say, this is wrong, and this is wrong, and this is wrong. That looks okay. And then they may even try to duplicate your experiments, right? That's what got those 2 Colorado scientists in trouble. They said they had cold fusion on their benchtop, right? So people tried to duplicate their experiment, right? Couldn't do it. One scientist finally said, all right, I'm going to figure out what went wrong with their experiment. In fact, he found out that they weren't measuring neutron flux from their reaction vessel. They were measuring ambient neutron flux in nature. So we didn't hear any more from them. I think they got canned. And that should happen to a whole bunch of other scientists too, especially the atmospheric scientists who claim global warming is destroying the world. But they've got too much political power and too much money's invested in it, so that's probably nothing going to happen to them. Anyway, so to answer your question is, not just one person determines whether this is fact or fiction. It's a community affair. Now, every once in a while, you get a scientist who can actually think, who can take bits and pieces of information from here and here and here and synthesize them into a coherent explanation. And then proposes it, and then everybody has to say, all right, here's what's wrong with it. Linus Pauling did that with The Nature of the Chemical Bond. He wrote that book based upon his experience, his experimentation, and that of others, put it together in a coherent message, and he got a Nobel Prize for it. Because not just the Nobel Committee, but the scientific community said, yeah, that makes a lot of sense. Your explanation is, I think, really what's happening. And in chemistry, in this microscopic world, we can't see what's happening. I mean, we can image atoms now, but we still can't image them in such a way that we can actually see these orbital interactions and all that stuff. This is just what we think is happening because it explains the evidence. Yeah. Okay, so now we've got this benzene ring, and we've got alternating double bonds and single bonds in a cycle. And based upon our work so far in conjugation, we know benzene is a planar molecule, and it has sp2 hybridized carbons with the extra unused, the p orbitals that go into the double bonds as written there. But we can also resonate that structure. All we have to do is move one double bond to its neighbor, and the other double bond has to move to its neighbor. So we get two equivalent structures resonating there. And that's why very often you'll see the benzene ring drawn that way. That's to show that it is fully conjugated. Only we give it a special name. It's called aromatic. Yeah. We also know this is true because the bond lengths of each one of these carbon-carbon bonds is exactly the same length. And it's not fully the length of a single bond out here or fully the length of a double bond here. It's somewhere in between. So each bond has pi character. All right. Let's see. Benzene is probably the most famous aromatic compound. We don't use it much anymore because it's carcinogenic. But if you have to, it's available. This is known as a cyclic pi system. So in this case, 6 electrons are shifted to convert the first resonance structure into the second resonance structure. So 3 arrows. Remember when we draw these curved arrows, if it's a double barbed head, that's 2 electrons moving. Right? Later on, I think when we get to polymers, you'll get the opportunity to use a single barbed arrow, and that's just 1 electron moving. But up to this point, we've only used double barbs.
Yeah. I remember talking about the single barb, but for the homework in the previous, it was
okay.
double barb.
Yeah. Okay. So what are the consequences of this delocalization? Right. We've already seen the advantages, the stability advantages to conjugated linear systems. But is there any further advantage to cyclic pi systems? I mean, does it stabilize even more? It's possible. Well, the molecule's symmetrical, right? It's fully planar. All 6 carbon bonds are equivalent, and they're in the same plane. And that's going to be one of the characteristics of aromatic systems. It doesn't have to be just one ring. You can have fused rings in a system, but they all have to be in the same plane because that's how you get the overlap of your p orbitals. They are unusually stable. So by that statement, I'm going to infer that these benzene systems or the aromatic systems are even more stable than conjugated systems. And we should be able to detect that with hydrogenation reactions if benzene will hydrogenate, catalytically hydrogenate. I think it will. All right. So okay. So here we're comparing a double bond in this 2,7-dimethyl-octofluorine 3,6-dione. We got that one double bond, and we know that we can brominate it, right? Molecular bromine, we'll put a bromine on one side and a bromine on the other side. We just got through doing one of those. If we try to do that to benzene, won't happen. It does not do that reaction. So that tells us that those double bonds in there are not real. They're not the same double bond as you would find in the molecule above. And they're unusually stable because brominating across that double bond in the first example stabilizes. It's lower energy. It stabilizes the product. So the benzene is so stable, it doesn't need bromines. In other words, it's not reactive in that respect. Now, one thing that benzene will do, if we have the correct Lewis acid catalyst, in this case, ferric bromide, Fe, iron 3 bromine. If we have that in there, then we can induce the molecule not to destroy its double bond and brominate across the double bond, but substitute the bromine for a hydrogen because we know that there's one hydrogen there. And we're going to substitute the bromine for that hydrogen. So these aromatic systems will do that. They undergo electrophilic substitution rather than an addition reaction. Because the pi system is so stable, it's not going to give it up. Now, we've looked at alternating double and single bonds in our common representation of a cyclic pi system. But does that automatically mean that your molecule is aromatic or is conjugated, is a cyclic pi system that's conjugated into an aromatic, right? And it doesn't mean that, right? Here's an example: cyclobutadiene. Resonance, although there may be some resonance involved, it doesn't stabilize the molecule. And one of the evidences for that is the bond length. Right? You have two bond lengths in this molecule. One of them is 132 picometers and the other one's 160. So they look more like double bonds versus single bonds. But you can still resonate one structure, that structure on the left, A, B, C, D, you can still resonate it with the double bonds here and then the double bonds here, but it doesn't conjugate. Well, that might not be correct. Because the author says this does not resonate. These resonance structures, these are not resonance structures. Well, anyway, this is a symmetrical molecule. So if you just rotate the molecule this way, it looks like the bonds have moved, but they haven't. Okay, so scratch what I just said. This molecule doesn't resonate. So we have alternating single and double bonds, just like benzene. But unlike benzene, this cyclobutadiene system, pi electrons are unusually unstable. And I suspect part of that instability is the bond angle. There is a strain in that bond angle because what's the bond angle? If these carbons are sp2 hybridized, then their bond angle should be 120 degrees. No, no. If it's sp3, it's 109.5. sp123. sp3 hybridized would be planar, be 60 degrees, right? No, 120. Yeah, 120, right? Because 120, 120, all the way around is 360. Okay. So we're expecting 120-degree bond angle, right, for an sp2 hybridized. But the bond angle in that square, or actually it's a rectangle, is 90 degrees. So there's a lot of strain. Should be 120. We've strained it into this square. Like I said, it's not a square. The reason it's not a square is because the single bond length is longer than the double bond length. So it's a rectangle. And that makes it extremely unstable. Right? It still has two different carbon-carbon bonds. So we should be able to carry out electrophilic addition with those double bonds. And what it would probably do is break the bonds, probably break the single bond too. Okay, let's see. We got a rectangle. All right, aromatic and okay. Now, aromatic comes from the root word for aroma. So benzene would smell. It would have, I think it's a kind of a sweet smell. So these compounds are called aromatic first because they smelled, but now they don't have to smell, right? There are other chemical reasons for calling them aromatic. Butadiene is anti-aromatic. That is, it's anti means against or opposite versus benzene. So aromatic compounds are cyclic pi systems that are unusually stable. So they have to meet that condition, obviously. Anti-aromatics are cyclic pi systems that are unusually unstable. So they're less stable than their linear counterparts. If we open that ring up, then it would be more stable than the ring system. Okay. Any other compounds are non-aromatic. They're not unusually stable or unusually unstable. So here's benzene, and we're going to use hydrogenation to show the difference between benzene and a double bond in a ring system. So the only way you can do that and compare the energies is for the benzene, you got 3 double bonds, theoretically. So you hydrogenate those 3 double bonds, and it takes high temperature and pressure to do this, right? So they don't want to go that route, right? You can't do it at room temperature. But once you do, you get a cyclohexane, okay? Now, the problem with that model is they're only showing the added hydrogens. Each one of those carbons has another hydrogen attached to it. And you get, this is exothermic, and you get 206 kilojoules from 1 mole of benzene being hydrogenated with 3 moles of hydrogen. Now, the only way to compare those is now to keep the bond hydrogen stoichiometry the same. So we need 3 moles of cyclohexene to give you 3 double bonds, and then 3 moles of hydrogen. And when you do that, you get a cyclohexane where you've 3 cyclohexane molecules where you've only added hydrogen across the double bond. And the exothermic output there is 356 kilojoules. So you get a whole lot more energy back, and it's the same concept, starting out at higher energy with the cyclohexene, and you're ending up at the same place as the benzene. on the benzene starts out at lower energy. So this hydrogenation is evidence for the aromaticity of benzene. That's a huge difference in the energy too. All right, so where does that put cyclobutadiene? Well, if we look at the cyclobutadiene has 2 pi bonds. So we would have to use 2 moles of cyclobutadiene. And let's see, let's see how we're going to do that. Oh, okay. So in the first part of the slide, we're comparing benzene with cyclohexene. In the second part, we're comparing cyclobutadiene with cyclobutene, right, with just 1. So there we only need 2 moles of each. 2 moles of each hydrogen, and 1 mole of the cyclobutadiene and 2 moles of the cyclobutene. And then compare those energies. And we find out that we get a massive amount of energy back from the cyclobutadiene as compared to 2 of the butenes, cyclobutenes. Right? So that means that the cyclobutadiene is extremely unstable. I wouldn't be surprised if it would probably be very flammable, but it might even be explosive. It's so unstable.
So that would mean it's like going back to last thing, it wouldn't be green.
No, it wouldn't be. I wouldn't think it would be green. No. Okay, so here's the explanation for cyclobutadiene's instability, and just compare the apples and apples. Right, the amount of energy required to add 4 hydrogens to 1 ring versus the amount of hydrogens it takes for 2 rings would give you the same product, cyclobutane, but the energy difference is massively different. All right. So this character, I don't know too much about Huckel. From the looks of it, he's probably German. But he put together this set of rules that help us determine whether a molecule is aromatic or anti-aromatic or non-aromatic. So I thought we had them listed. Yeah, we do have the rules listed. We just talk about them here. Aromatics have a cyclic pi system, right? Alternating double and single bonds, more than likely. I don't think you can have a triple bond in a cycle system. No, its hybridization wouldn't allow it. So it's always going to be a double single bond arrangement. So you have this cyclic pi system, and you have an odd number of pairs of electrons. So what does that mean? Well, let's look at it this way. If n is 0, 1, 2, 3, or 4, then an odd number of pairs would be times 2 of each one of these. Right? So that's the number of electrons. Right? An odd number of electrons would be, well, that doesn't count. And this would be 2. This would be 4. This would be 6. Well, let's see. Okay. Forget that. God, there's a better formula. I thought I was going somewhere with that, but I'm not. We need an odd number of pairs of electrons. So we need 1, 3, 5, 7, 9, 11. Almost all of those are prime numbers. How about that? You need that. You need a cyclic system. You need an odd number of pairs of electrons. If it's anti-aromatic, then you will have that cyclic pi system, but you'll have an even number of pairs of electrons. So you have a 1 pair would be 2 electrons. 2 pair would be 4, 2, 4, 6, 8, 10. That would be anti-aromatic. Everything else is non-aromatic. Okay, here's Huckel's rules. Um, they all the atoms in the ring must be in the same plane. It has to be a planar molecule. Even if you have several fused rings together, they all must be in the same plane. And we know from past discussions that that's so that the p orbitals can overlap. Right? If we have a kink in there, like if we had cyclohexane, right? It could be a chair or a boat. Right? That's not planar. The second rule is we have to have that odd number of pairs of electrons. So 3 pairs would be 6 electrons. Actually, I did include 6 in that last one, right? Anti. So 6, we have to count 6 out. So it'd be 2. Actually, 2 would be right? Odd pair, odd numbers pair. 1 pair would be 2. 3 pairs would be 6. 5 pairs would be 10. Okay, so uh, I better leave that alone for now. So we have to have that odd pairs. Each anti-Huckel number contains an even number of pairs. So 2 pairs would be 4 electrons, for instance, in the system. Here's the formula. So this is the Huckel number, 4n plus 2, where n is an integer greater than or equal to 0. So if we count the number of electrons in the system, 4n plus 2 would have to be well, this is a Huckel number. It has to be this number of electrons in order to be aromatic. So if it were 0, if n were 0, then we would have two electrons. If n were 0, we have 2 electrons. If n were 1, we'd have 6 electrons, right? 1, 4 plus 2 is 6. If we had 2, n were 2, then we'd have 8, 9, 10. There we go. Odd number of pairs. So 5 times 2 is 10. 3 would be 14 electrons in the system. You just keep going. Anything else, anything besides 2, 6, 10, 14, and on, is anti-Huckel numbers. Now, I'm not saying it's anti-aromatic. I'm just saying it's anti-Huckel. Okay. So, does benzene meet that criteria? Well, it's planar, right? It has alternating double and single bonds. It has 2, 4, 6 pi electrons. Now, let's go back. All right. Oh, that makes sense, right? Look at the pi electrons. Those are the only ones that can contribute because the other electrons are locked into sigma bonds. So 2, 4, 6. Yep. We got 6 electrons in the system. So we've satisfied that condition. How about cyclobutadiene? It has 4 electrons. Nope. It's anti-Huckel. I don't know why they put this one, hexa 135 triene. Well, we have 3 double bonds and we have 6 carbons and we have a Huckel number, right? But we don't have a cycle. So it can't be aromatic. It's non-aromatic. It's conjugated, non-aromatic. It can have the Huckel number, but it doesn't have the other conditions. So it's non-aromatic. I'm not sure what Cardi's getting at with this one. There are the rules. So if we use step one for each one of these, maximum electron movement is depicted by the curved arrows. Okay. Curved arrows. All right. Step two, all six atoms of the ring for benzene are involved in the ring are planar. So the pi system is cyclic. Okay. For cyclobutadiene, all four atoms of the ring are involved and the ring is planar. So the pi system is cyclic. All right. We met that condition. All six atoms in this last molecule are involved, but the atoms do not make a ring. So the pi system is acyclic and the species is non-aromatic. So that's where we leave off with C. C's out. And we go back to step three. The curved arrows represent 6 electrons, a Huckel number, so that is aromatic. Okay. And the curved arrows represent 4 electrons, an anti-Huckel number, so the species is anti-aromatic. Okay, I think I see what he's getting at. If we want to resonate our structure, then we draw the curved arrows to show the movement of the pairs of electrons. Right. And then that tells us how many electrons are being represented. Maybe that approach would be better for some molecules, some that don't look aromatic, and we can't tell just by looking at the structure. We need to be able to move the electrons to resonate. So maybe Cardi has a better idea here. We'll try it out on some other molecules. Like this one, heterocyclic aromatics. Heterocyclic simply, I mentioned that once before when we were talking about furan. That's tetrahydrofuran. This is furan. This is a heterocyclic. A homocyclic means every member of the ring is the same element. This one has oxygen stuck in there instead of carbon. That's heterocyclic. In this case, pyridine has nitrogen stuck in there with the double bonds. Now, can we move those pi electrons? Yeah. Yeah, we can move those pi electrons around there. And the lone pair is actually in an isolated pi system. It's isolated from the pi system, excuse me. So we don't have to consider that lone pair out there. It's perpendicular. It doesn't resonate. So we got 1, 2, 3 arrows moving. That's 6 electrons. That's a Huckel number. So pyridine is aromatic, which means it's very stable. Let's see, parole. All right. 6 electrons occupy this cyclic pi system. The lone pair resides in a p orbital and is therefore part of the pi system. So how do we know that it's in you have to get that from some other investigation, some other workup to know that the lone pair on that nitrogen is available and the lone pair on the other nitrogen and pyridine is not available. That's probably why they wrote it on top of the nitrogen to show that it's parallel with the other p orbitals. But we got the Huckel number again. So now why did okay, I see the curved arrow from the lone pair goes to the bond. So does that make a double bond on the nitrogen? And then the double bond goes to the flat side on the left. That makes another double bond. And then we've got a pi pair of electrons on that other one that's going to the carbon itself. All right, we're saying that it's aromatic. How about furan? Well, yeah, we've got Hooker numbers on all three of them. So they should all be aromatic. Now, is that on the next slide? Okay. Ions and aromaticity. All right, we just blew that one off. I'm assuming, based upon what we've seen there with the arrow movement, that we have three aromatic compounds. Although it's not real clear how that happened with the last one. Cyclopentadienyl anion, right? We got that lone pair that can move. All right, so we got a Huckel number for A. How about for B? We got yeah, we've got electrons moving there. 3, 6, yeah, 3 pairs moving. How about that cyclopropanyl anion? We've only got 2 moving, 2 pairs moving, so that's anti-aromatic. It's not always straightforward in my mind how to determine aromaticity. Some are easier than others. Let's put it that way. How about this? Uh, is this system aromatic, anti-aromatic, or non-aromatic? We assume the molecule is planar. Okay. So here we've substituted sulfur for an oxygen. So if this is furan, what would that one be? Thian? Yeah, that works for me. All right. So we're moving a lone pair and pi pairs. So if we do that, we should have a Huckel number. So we're saying that the system is aromatic. Note that for the ring to be aromatic, the external carbon-carbon double bond is effectively treated as a separate pi system. All right. It may be only one single bond away, but since if we look at it 2 different ways, right? Look at it as whether we're conjugating one of those double bonds in the ring and the double bond outside the ring, does that add to stability? And no, it doesn't, because it would destabilize the ring when we do that. So everything that happens there happens inside the ring, and that external double bond is isolated. So we do have an aromatic system there. How about larger rings? They're identified as annulines. And the N is just how many carbons are in the system. So a 4-annuline is the cyclobutadiene. Okay. The 6-annuline is benzene. And then we can have a bigger one. The A is a huge, it could be a huge molecule. Let's see, we got an example here. 1, 2, 3, 4, 5. Oh, it's a stop sign, so it's got 8 carbons in it, right? 2, 4, 6, 8. Yep. So this cycloocta-1357 tetraene is an 8-annuline. It should be anti-aromatic, but only if it's planar. And we know that it's not planar. The reason we know that is from physical evidence, right? Experimentation. So it's got that boat conformation. That means that the p orbitals are not parallel to one. So this one is non-aromatic. It's not anti-aromatic. It's yeah, it's non-aromatic simply because planarity trumps Huckel number. This first one on the left, biphenyl, where the two rings are connected only through one carbon from each side. So that effectively isolates the systems. We've got two aromatic systems here, right? One benzene ring on one side, one benzene on the other. Naphthalene is a fused ring. So in order to fuse rings, you share two carbons or two atoms from one ring are present in the other ring. And if we move electrons like Carty wants us to, then what could happen? 1, 2, 3, 4, 5. 5 pairs moved. That's 5 odd pairs. Is 10 electrons. That's a so naphthalene is aromatic. It also smells. Naphthalene. Yeah.
Is it is it like just like kind of like ammonia like deep smell? Is it kind of more acidic?
It's more subtle than that.
Yeah.
Right. Naphthalene was once used as a what do you call it? Moth repellent.
Oh, the mothballs?
Yeah, you put mothballs in.
Yeah.
Now there's another one. I can't remember which one it is. But they're both aromatic. I mean, they're both smell.
Yeah.
And they keep the moths away from the clothes. Anthracene is like naphthalene, or we fused another ring. So if we move our electrons, like Carty wants us to, with our curved arrows, 1, 2, 3, 4, 5, 6, 7, that's an odd number. 7 times 2 is 14. So that's a Huckel number. Anthracene is also aromatic. I think anthracene was isolated from coal. Pretty sure it was. One of those breakdown products. Naphthalene probably was too. Okay. Is this one aromatic, anti-aromatic, or non-aromatic? Well, let's see. Is it planar? Not sure. It looks like it's got conjugated system available. Right. Um, it has a cyclic pi system. So should we assume that it's planar? Um, yeah, we have to assume it's planar. Otherwise, we're just dead in the water. So if we assume it's planar, then let's move our electrons. 1, 2, 3, 4, 5. 5, that's odd pairs. This should be aromatic. 10 is a Huckel number. Now, did it actually tell us that it was planar? It didn't. So we have to assume it's planar. I mean, otherwise we're stuck. All right. Now, Carty wants to talk molecular orbitals. And I've never been comfortable with the way he approached it. I think he assumes a lot of things. But we can say some things about in terms of constructive and destructive interference, because those characteristics of when we take all the electrons in a molecule and combine them and their orbitals and produce a molecular orbital system, then we get bonding versus anti-bonding orbitals. Remember that much?
Okay. Yeah.
And that's due to three-dimensional constructive interference or destructive interference. Destructive interference produces nodes where we're expected to have no electron density. Or actually, it produces got the term. Not anti-bonding. Bonding versus anti-bonding orbitals. Right? And we designated those, right? A sigma bonding is like that. A sigma anti-bonding is like that. Remember those symbols. Yeah. Okay. So a node appears where there's complete cancellation of the resulting molecular orbital. There's zero probability of an electron in a particular orbital existing at a node. All right, so those are general characteristics of molecular orbitals that are constructed from atomic orbitals of the contributing atoms in a molecule. So for this, an acyclic pi system. All right, so that's like our, like these types of molecules. Here, there, something like that. Conjugated systems, not aromatic. Draw the lowest energy pi molecular orbital. So the same phase, only constructive interference. All right. This is where he loses me. Draw the next lowest pi molecular orbital. Which leads to a node. Okay, when you cross a node, the phases have to change. So the way he draws those is, since we're talking about overlapping p orbitals, then we have these p orbitals side by side, and we designate the phase like that. Say, if we cross over, and we have flipped the phase for the next group, then that gives us a node where there's no electron density there. But if we go to the next one and it's in the same phase, then there's no node there, and those can overlap. Okay. Nodes have to be placed symmetrically. It's actually, yes. If there's an odd number of new nodes for a particular pi molecular orbital, then one node must appear at the center of the species. All right. We need examples. For any node located on one half of the species, there must be a corresponding node located on the other half of the species. So each node in the pair is the same distance from the center of the species. All right, so here are our examples. We have destructive interference for that one. Let's see. If we did this, and we get his first example, like that. Okay. That's pi 3 contributor. All right. So the pi 2 atomic orbital contributions, we've got a node on the carbon. No contribution by the p orbitals on carbon 2. Okay. And then if we have them all aligned in the same phase, we have no nodes. So what's he saying? Those are the three possibilities for an allyl cation, where we have 3 carbons. We have complete constructive interference, which produces, okay, so the bottom one gives us the conjugated system, whereas the top 2 ones give us no conjugation because there are nodal planes. Okay, that's as simple as I can make it. Now, if we have electrons, based upon what I know of molecular orbitals, if we have electrons in the bottom ones where we have constructive interference all the way across, we have overlapping, gives us the conjugated system. If we have electrons in those and no electrons in the others, then we're good to go. If we have electrons in the non-conjugated, the ones with nodes, then we can't have more in those than we do in the conjugated system. Because if we calculate the bond order, we can't have a 0 bond order, and the greater the bond order, the better. Okay, so these are apparently the 3 possibilities. molecular orbital energy diagram. The ones where we have two nodes are higher energy. The one where we have one node is middle energy. And the one where we have no nodes, we have the possibility for bonding. And that's where our electrons are located. All right, that's about as far as I can go without hurting my head. Unless he's going to explain it further. Principles of molecular orbital energy diagrams. Each sigma bond in a Lewis structure represents a pair of electrons occupying a sigma bonding molecular orbital. There's one sigma star antibonding molecular orbital. All right. The sigma tend to be, we're just rehashing, right, what they mean in terms of energy. Usually, when we used diatomics before, like we had two hydrogens, and we would form this sigma bonding orbital and then be the sigma star antibonding orbital. If you have not hydrogen, but say you have oxygen, and you have the opportunity to put, let's see, would that be right? Oxygen might not be a good choice, say nitrogen. Then we would have these pi bonding and pi antibond here. Right? Then you put your electrons in. Generally, the sigma star is higher energy than the pi star, unless you get SP mixing and then they flip. Okay. I thought we were just looking at this one. Okay. So the highest occupied molecular orbital. All right. If we've got 14 electrons occupy these molecular orbitals. Well, pi's usually come in pairs. All right, so we should have two pi orbitals in there, shouldn't we? 7 sigma molecular orbitals. Oh, okay. 7 sigmas are down here lower in energy. Then we get to the pi's. And then sigma stars are on top. I see the way he's arranging this thing. We're letting those just sit there because they're not part of the pi system. So the sigma molecular orbitals down below and the sigma star molecular orbitals above are created, but we haven't put electrons. Well, we put 14 electrons in the 7 sigma molecular orbitals. What does that leave for us? Well, let's see. If we have 3 carbons, let's see, 1, 2, 3, 4, 5 hydrogens. So that's 5 electrons for the hydrogens. And then we have 3 carbons. 3 carbons would be 6. 3 times 6 is 18. And then we have the lone pair. So that's 2 more. So we have 25 electrons that we have to put into the system. All right. 14 of them have already gone in. So that's 11 electrons left over. All right, something happened. Oh, carbon's 4.
Well, I thought it was 6.
No, that's oxygen.
Oh.
Carbon's 4, sorry. So this would be 12. So that's 14, 19. There we go. So we have not 11 left over, we have 5 electrons left over. Okay, so they would go into that first pi orbital, and then we put 2 in there, then 2 in the next one. Now we have 1 left over. Where does it go? It has to go in the antibonding. Right? If we put them in, what's the term for it? It'll probably come to me later when I'm not trying to think about it. Um, so this is a different system, right? Butyl 1,3-diene. If you don't mind, I'm not going to stop here. Okay, the Frost method for energies of cyclic pi molecular orbitals. Draw a regular polygon that represents the cyclic compound's line structure. Okay, I can do that. Orient one vertex of the polygon directly downward. Add the non-bonding energy. Draw a dashed horizontal line through the center of the polygon. So if it were a 5-membered ring, we draw it like this. And then we draw a dashed line here. If this scale is the energy, we draw it like that. Representing energy of the non-interacting p atomic orbitals. So this is the energy level for all the p orbitals that went into the system. And now the molecular orbitals are, place the energies of the pi molecular orbitals, draw a short, solid horizontal line at each vertex of the polygon. Each line represents the energy of a pi orbital. So we would have this one would lead over here. These two would lead to two of these. These two would lead to two of those. That's the Frost method, the way I understand it. Now let's see if the picture says the same thing. Yeah, there you go. Well, they put their lines on the, yeah.
I get it. I know what you mean.
Okay, so now what do you do? Well, anything below this line is bonding. Anything at the line is non-bonding. And then anything above the line is anti-bonding. So these would be non-bonding. If they're at the same energy as the atomic orbitals, they're non-bonding. Okay. So that's why, okay, this is why benzene is so stable, right? Our example here is benzene in an energy diagram with molecular orbitals. We've got 6 pi electrons that are in the system. And if we put them into, well, that's not the right example. We've put those in, they have to go in to the lowest orbital first. That's the Aufbau principle. Aufbau means lowest energy first, and then you move your way up. So we got all of our 6 electrons, right? 2 in each orbital are bonding. And we don't have any anti-bonding. So that makes benzene extremely stable.
Is it because it's like when you look at the ring structure, like it just looks like, I don't know, proportionate almost. Is that like kind of why too? Like because it looks, I don't know. Like when I look at it, I see it proportionate, like you know, like it doesn't in my head it's different. Just scratch what I'm saying. It's working in my head, but I don't know how
Okay.
to say it.
Yeah, I never hitched onto that wagon.
Yeah, that's okay.
Okay, how about nodes in a cyclic pi system? Each pair of degenerate molecular orbitals has the same number of nodal planes perpendicular to the bonding axis. What does that mean? The energy of each molecular orbital rises with each additional nodal plane. Okay. So if you got no nodes in there, that's lower energy. If you got one node, it's the next highest energy. If you got 2 nodes, it's higher energy. That's what I'm seeing. So A down here represents the lowest possible energy, right, for those 2 electrons. And then these pi orbitals here, I don't know, I guess from your previous class, degenerate means equal energy. It doesn't mean perverts. So in these pi 2 and pi 3, they have one node in, right? So you still get interactions among those pi's, but they can't cross over the node. And then, of course, once you get to the pi stars, you start adding nodes. And those nodes make bonding unlikely. All right, how about the cyclobutadiene? Why it's anti-aromatic. All right, if we do this Frost method, and we take the butadiene and we turn it on its edge. So now we get like this, that, that. Right? And there's the line. That's the atomic orbital energy. Then we've got one here, got one here, there. These are non-bonding. This is bonding. This is anti-bonding. So how many electrons do we have? Well, we got 1, 2, 3, 4, right? 4 electrons in the pi system. 2 of them go down here with opposite spins, and then one goes here and one goes here. Let's see if I can remember the name for that. It's not coming to me. For degenerate orbits, you have to have electrons in separate sublevels until you filled them up, and then you can start pairing them. But I can't remember the man's name that's named after. Okay, so what does this show us? The energy diagram obtained here shows that the 4 pi electrons in cyclobutadiene occupy pi 1, 2, and 3. Pi 1 molecular orbital is completely filled, whereas the pi 2 and pi 3 contain only 1 electron each. All right, that doesn't explain it. Hopefully this will explain it. Okay. We've got pi 2 and pi 3 have 1 node each, whereas there are no nodes in the pi 1. Lowest energy has no nodal planes, all right? And each additional nodal plane raises the energy of the other molecular orbitals, all right? So I'll go with that. But how's that explained? Why it's non-aromatic? Anti-aromatic. Doesn't. There must be something else in the text that I'm not getting. I mean, we followed the rules and found it's anti-aromatic, but this doesn't explain that it's anti-aromatic. Right? What would its bond order be? It'd be 1, 2, 3, 4. 4 minus 0 for antibonding divided by 2 is 2. So its bond order would be 2. All right. Well, they're going to talk about DNA now. DNA has lots of aromaticity in it. In fact, we looked at one of them already. Well, no, that's not right. These are these nitrogenous bases in nucleic acids. And did you get any of that in you've had a lot of biology. They talk about this in biology class. Sometimes they do and sometimes they don't.
I don't think so.
Okay. You'll definitely get it in biochemistry.
Yeah.
So the DNA molecule is a double helix. We've got 2 strands that snake around each other, and they're held together by hydrogen bonding between the bases. But within the chain, of course, you've got all covalent bonds. And these nitrogenous bases that are the foundation for the code in the DNA are all aromatic. So they're very stable, which is good. If they weren't stable, then our cells would probably be in trouble.
Yeah. But isn't that what happens really when, like, cancer and stuff like that? Because they're not really stable. So they're.
All right. Well, what cancer does as a general outline
Yeah.
is it causes the cell to lose its control system. And that's an as I understand it, largely due to its effect on the DNA and RNA of the cell. So it has no control over its growth, so it just grows out of control, and it consumes all resources as it goes. I had a dog passed away not too long ago. He had lung cancer, and she would eat and eat and eat and lose weight because all the energy she was taking in was going into feeding the cancer. And I asked the vet, I said, when will I know it's time? She says, when she stops eating. So one day she turned her nose up at her food, and the other thing, she was really sick. So I knew it was time.
Yeah.
She was a good dog. She was a stray, Corky. Um, she had kind of short legs, but she was hefty body. We think that she was a mix between maybe a Basset Hound and a Feist.
Yeah, I had a Basset Hound.
Okay, back to the topic here. So all these bases are aromatic. And if we count up the pi electrons, they're all planar. We count up the pi electrons. The adenines and the adenine and guanine are fused rings, and they're all planar. So they have 10 pi electrons, and the cytosine and thymine have 6 electrons. So they have the Huckel numbers. All right. So the way they interact in these systems is one purine and pyrimidine. Purines are the bigger molecules. So the guanine, purine, interacts with the cytosine. Guanine and cytosine interact on that thing here. So guanine and cytosine, you see here, you have the red and the orange. They're interacting through hydrogen bonding. And that's so that the code is the sequence of bases. And in order to access that code, since it's internal to the molecule, you have to pull the molecule apart to read the code. So the hydrogen bonds are just strong enough to hold it together until you need to read it. And then there's a special enzyme that comes in and opens it up so that it can be read by um, a transcription, a tRNA, a transfer RNA. And then it takes it outside the cell and goes to a ribosome usually and manufactures the protein. Adenine and thymine, then they interact through hydrogen bonding. And on the next slide, I think we show you, yeah, here we go. So the guanine and cytosine interact through 3 hydrogen bonds. And the adenine and thymine interact through 2 hydrogen bonds. So we have the sugar phosphate backbone. So you're going to have, for DNA, it's deoxyribose, and then a phosphate. So you have deoxyribose, a phosphate group, and then deoxy, all the way up the chain. And then out connected to the sugar are your bases. And then they do their hydrogen bonding with the other chain. Now the RNAs, to my knowledge, they don't do the double helix. They just have a single helix, but they're stabilized with hydrogen bonds. DNA is sort of a permanent repository of information, and RNAs are more of the worker bees, the soldiers. So they stay open all the time. Okay, what are the consequences of aromaticity in DNA? Well, we're not telling you something you don't already know. Each base is planar. The geometry allows them to pack efficiently inside the double helix. All right, so if they're planar like this, you can get them really close together and get a lot of information in a short distance. Let's see. This is just a 3D model on the right. Oh, that's interesting. I never saw that before. Pi stacking takes place inside the double helix. So you get the hydrogen bonding between the bases of one strand and the other, but they are also so close together in planar that you get interaction between their pi systems. So that further stabilizes the whole molecule.
Seems like
Yeah, I don't know how they figured that one out.
yeah.